Hello students. So in the previous class we started with singular perturbation because we slowly want to motivate the concept of stiff differential equation. Now in singular perturbation we saw some definitions and we also learnt about one example where we saw that how does these singular perturbation bring different characteristics to the solution. Motivated from the similar example, we will continue the definitions of slow and fast time scales, right? And how do we motivate the idea of these two time scales? So let us say we are working with a similar problem that we or example that we had in the previous class, and in the same example, it is the continuation of the same example. So replacing replacing T by epsilon by tau, we obtain the ODE, di tau by d tau equals to I tau plus cos of tau by epsilon. Let us call it as equation number 1, today's presentation. Note that, however, that time scale, that the slow time scale, that is the one that properly describes the slow motion or slow solution. The slow solution is of course still a factor 1 by epsilon larger than the fast time scale, right. So it basically the slow time scale where we had epsilon times t, one that properly describes the slow solution is definitely that t is definitely larger than 1 by epsilon factor of the fast solution, right. So this fast scale is actually given by our tau. So when you multiply tau, which is epsilon, which is basically t by epsilon, right. So if you say t represents the slow time scale, so then t by epsilon will represent the fast time scale. So obviously it is larger than 1 by epsilon scale factor. Now then in many practical application we often find the dimensionless parameter which indicates the presence of multiple time scale are therefore required a careful consideration, right. So basically we write the ODE. So we write the ODE as epsilon times x dot of t. So it should not be epsilon, it should be t. This should be t and this is x epsilon because it is depending on epsilon, equals to minus of x epsilon plus bt, where b is any function of t and x epsilon at 0 is equals to x 0. So this is our same example, that electrical example, is just that we have now used a general x epsilon, right, because usually when we write dx dt to represent ODE, that looks quite familiar to us. Okay, so let us call this as equation number 2, where 0 less than epsilon less than 1 or epsilon very less than 1 and b belongs to C1. C1 means set of all continuously differentiable function once actually. So that means the dB dt exists, and this singularly perturbed ODE in fact shows several features of interest, like what? So if we take epsilon equals to 0, we obtain the solution of the reduced equation, reduced equation x0t equals to bt, right? Because if you substitute epsilon equals to 0, so this first order term will vanish, and therefore you will end up having x epsilon, where epsilon is 0, so you bring it on the left hand side and then we will get this. So this is our equation number 3. If bt is of order 1, then epsilon times x dot 0t equals to epsilon times b dot t. That means we are taking the derivative. Since this is of order 1 and this is epsilon, so basically it will become of order epsilon, and it does not satisfy the initial condition, does not satisfy the initial value at t equals to 0, right? Because this epsilon times x dot 0 is actually becoming of order epsilon, and therefore it fails to satisfy the initial value at t equals to 0. Hence we have a small region, the initial or boundary layer, whatever, boundary layer, where epsilon into x dot of epsilon t is becoming of order 1, right? And the width of this layer can be found easily. If we have a small interval, interval 0 to, let us say, phi of epsilon, so the interval depends upon epsilon also, say, then bt is nearly constant. There, that is bt, there should not be any dot, bt equals to b0. So we have approximately, epsilon times x epsilon dot equals to x epsilon plus b0, and x epsilon at 0 equals to x0. This is equation number I don't know, 3 or 4, 1 2 3 4. Okay, and the solution of this equation can be obtained very easily. So from here we will get the solution as x epsilon t equals to x0 times e to the power minus of t by epsilon plus b0 1 minus e to the power minus of t by epsilon. Let us call it as equation number 5. So clearly, when t is greater or equal to epsilon, the first term becomes becomes less important than the second, because it will simply just be epsilon 1 x 0 by epsilon, whereas the second term, when t is the second term, the first term becomes, I don't know why did I write g, the first term becomes less important than the second one, and hence we may take phi epsilon, that means the end point of that interval as epsilon, and in the layer we have the so called boundary layer, correction term, boundary layer correction term e to the power minus of t by epsilon. So basically the from here we can see that the observation can be generalized, and we can write an equation of the type epsilon times x epsilon dot equals to f of x epsilon. Right hand side will be a function of x epsilon, where 0 less than epsilon less than or equal to 1, and x epsilon at 0 is equals to x 0. So the reduced problem, let us call this as equation number 6. So the reduced problem can now have more than one solution, to be found, from solving f at x 0 equals to 0. And if we are interested in stable roots, then we will do the del f by del x. If it is less than 0, then we get the stable, and so on. So, and if we are interested, if we are interested in the stable root, at x 0, in the stable root at x equals to x 0, then del f del x must be less than 0 at x equals to x 0, right. So basically this can constitute a small theorem. We will state it without proof. Suppose you can look into the textbooks which we have mentioned at the beginning of this lecture. There you should be able to find the proof. So suppose the equation f x equals to 0 has at least one stable root phi. Denote the immediately preceding and following roots as phi 1 and phi 2 respectively, that is phi 1 less than phi 2, if phi 1 or phi 2 does not exist, we take phi 1 equals to minus infinity or phi 2 equals to plus infinity. If phi 1 less than x 0 less or equal to phi 2, then the solution x epsilon t of 6 exists for t greater or equal to 0, whereas limit epsilon tends to 0 x epsilon t equals to 0 where t is positive, right. So, this particular theorem actually tells us the property of the stable root for this general perturbed equation epsilon into x epsilon dot equals to f of x epsilon and x epsilon at 0 equals to x 0. So, from there what kind of behavior of the solution that we can draw as epsilon tends to 0. So, here we can see that basically depending upon the the roots of the f of epsilon x or f x epsilon, we can determine whether the solution behaves, in what way the solution behaves, right. So, this is a small result that is there. I mean, you can look into the proof if you like. Now, let me just introduce another terminology, which is basically matched asymptotic expansion, right, and then we will slowly move to stiff differential equation. So, matched asymptotic expansion. So, the different time scales, the different time scales require different approximation, require different approximations, right, approximations. Here we shall see how this should be done when the power series expansion in epsilon are employed. That means we have the solution, which of course depends on this scale parameter epsilon. So, basically we will do a power series expansion of this solution in terms of epsilon, and then we will investigate how this different time scales actually gives us the different behaviors of the solution, right. So, the idea is to use the expansion inside and outside of the layer regions. The idea is to use different expansions inside and outside the layer regions, and match the approximate solution appropriately, approximate solutions appropriately. Right. So, what do we mean by this asymptotic expansion? Let us see one example. Example 1. So, consider this integral e of x equals to integral from x to infinity e to the power minus t by t dt, where x is positive, right. So, here we can do the integration by parts, and the integration by parts will actually give e of x equals to e to the power minus of x by x 1 minus 1 by x plus factorial 2 by x square minus factorial 3 by x cube plus dot dot and so on, plus minus 1 to the power n minus 1 factorial by x to the power n minus 1 plus Rn x term, some remainder term, right, where Rn x, the remainder term, is given by minus 1 to the power n minus 1 factorial integral from x to infinity e to the power minus of t by t to the power n d of t, right. So, this is more or less the solution of that integral. So, now we cannot let n tends to infinity since the series is not convergent, right. This can be proved that it is not convergent, and but it is still a useful expression, right. So, if it is a useful expression, we want to use it for larger x. So, we want to use this expression for larger x, and so we are defining epsilon equals to x to the power minus 1. So, then when x is large, epsilon is small, right, and E epsilon is equals to e to the power 1 by epsilon, capital E of 1 by epsilon, right, and we find that E of epsilon is actually epsilon minus epsilon square. So, just substitute the values, and this will be 2 factorial by times epsilon cube minus 3 factorial epsilon to the power 4 dot and so on R n bar of epsilon, where R n bar of epsilon equals to minus 1 to the power n minus 1 factorial e to the power 1 by epsilon, integral from 1 by epsilon to infinity e to the power minus of t by t to the power n dt, and also R n bar epsilon, if we take the mod on both sides, this will be less than or equal to n minus 1 factorial times epsilon to the power n. Hence, now if we keep n fixed, we conclude that R n bar epsilon exponentially converges to 0. As epsilon tends to 0, right. So, this is basically via the help of this asymptotic expansion or just a power series expansion of epsilon, we can keep the n fixed, even we can have a larger values of n, and this R n bar of epsilon will converge to 0 as epsilon tends to 0. So, the above example induces the following definition of an asymptotic expansion. So, the above example induces the following definition of an asymptotic expansion. So, let x epsilon belongs to R n be a quantity, we would like to approximate and let xj, where j running from 0, 1, 2, 3 and so on, be such that for each small n belonging to set of a natural number, norm of 1 by epsilon to the power n plus 1 x epsilon minus summation j running from 0 to capital N epsilon j x j norm is bounded for epsilon going to 0. Then summation j running from 0 to capital N, j running from 0 to j running from 0 to infinity, epsilon j xj is called an asymptotic expansion for x epsilon, and as a consequence we have for each n, for each small n, for each capital N belonging to set of a natural number, x epsilon is equals to summation j running from 0 to capital N epsilon j xj plus order of epsilon is the order of n plus 1, right. And the method this may be the correct asymptotic expansion for x epsilon, so that you get the this asymptotic behavior of this solution as epsilon tends to 0. The method basically of matched asymptotic expansion, asymptotic expansion for expansion is a collective terminology, for a number of techniques, So this is widely used in different branches also. So in second order ODE, when you are finding the when you have a singular points and when you are looking for series solution, there also we use the asymptotic expansion. If you read further advanced into PDEs, then you come across a topic called homogenization theory. There also we use asymptotic expansion, where you write the solution in terms of a power series, and from there you equate the coefficients of epsilon and so on. So the definition asymptotic expansion, it's a very general terminology, but it is used in different context. Basically the problems from ODEs and PDEs, but it is used in different contexts. Depending upon the requirement, we adapt this power series expansion into different contexts, right. And another definition from here, that is something called outer solution. So we call a solution outside the layer, the outer solution. Call a solution outside the layer the outer solution, denoted by x epsilon t, and assume the asymptotic expansion to exist, and assume an asymptotic expansion to exist, which is of type x epsilon t is equals to summation j running from 0 to infinity epsilon j xj t, right. So this is what we mean by the outer solution. All right. So we have learnt or we have seen the ideas behind singular perturbation, and how do we motivate that to this electrical problem that we saw. And from there we also learnt about matched asymptotic expansion, and how this asymptotic expansion can be understood to know the behavior of the solution, which is dependent on these small scaling parameters. We also learned about fast time scales and slow time scales. Now we use these ideas to motivate the concept of stiff differential equation. So we'll start with stiff differential equation in our next class. So I'll stop here today, and we'll continue our discussion in the next class. Thank you.